All right, hi all, it's Mr. Yeager for Honors Chem. We are moving into now complete and net ionic equations. All right, so this is where, I keep on saying this is the next big step, but this is just another kind of organization of a chemical equation, a chemical reaction, where we really want to show what's going to happen and what we might see, what is actually changing places, what is actually forming, etc., etc. Because in some of the cases, we might just have a bunch of ions that all split up, but they don't actually come back together and form anything new. We just separate all of them and then they're all just everywhere. So this is where we are really showing the atoms and the ions involved with the chemical reaction. So to kind of review everything we've done so far, we have our chemical equation, we have balanced it, we have predicted the products, we have identified the type of reaction. So our next part is going into net ionic equations. So the first thing we have to understand, though, is what are called solubility rules, which you can see I have over to the side here, so I'm trying to show as many as possible. There are more solubility rules than this, all right, but this is generally the one we are going to be looking at. There are some on here that we have to be able to remember and memorize some, okay? Well, these rules are showing what compounds or elements will always create an aqueous solution, will always be in ionic form when they're placed in water. All right. The reason we have these is this will help us show when I have a chemical reaction and the two chemicals, the two reactants are initially in aqueous solution, so that both of them are dissolved, after I mix them to determine if any solids will form. All right. And so I'm not going to read every single one of these. We should basically understand this first one here. Essentially, all the alkali metals and ammonium are always soluble with whatever they combine with. Regardless of what the anion is, alkali metals and ammonium are always soluble. All right? It turns out that nitrate and acetate are always soluble. All right? So those are some that we really need to kind of make sure we feel comfortable with. From there, then we get to ones that we kind of have to look a little bit more carefully at it. The halogens, which all would be dissolved with anything above with any alkali metal or ammonium. Most halogens will dissolve except when they're basically with almost essentially a transition metal or any of like lead, okay, and lead as well. So again, some of the ones that aren't listed on there would be copper, okay, that one would not dissolve very well, but you know, certain other, and that's the issue, I said transition metals. Certain transition metals will dissolve with the chlorides, bromides, and iodides, like iron. So we'll stick with what's listed here. If we run into any that are not listed that might be insoluble, I'll make sure that's kind of clear. That'll be kind of mentioned in the problem itself. So this one's insoluble with, the halogens are insoluble with silver, mercury, and lead, but then soluble with any other ion unless I specifically tell you. Sulfate, again, you can read the rest from there. You have the list where you got to make sure you read it, okay? Well, where sulfate's saying all of them are, everything is soluble except for these, while the rule above it is saying everything is soluble except for these, okay? You know, or these are insoluble and then everything else is soluble. So sometimes they kind of have a reverse thinking on it. So anyway, you'll have that with you for some time. Some of the rules will be eliminated when it comes to a quiz or test, like the top two. Some of these other ones I will still give you as you move forward, but they'll help us show whether something will precipitate out. Okay? Some terminology to understand. When I say net ionic equation, that is a balanced chemical equation that's only showing the ions or compounds involved in the reaction. All right? Again, the objects either have to be ions in aqueous solution that are not on both sides of the equation, so they only show up on one side, and then any compound that's a solid, liquid, or gas, we write that out as well in the net ionic equation. Okay? And that's said in the second part, the complete ionic equation. That one's kind of the step before the net ionic equation where it shows everything, even in the ions, where you're going to see them on both sides of the reaction before we cancel them out. So in net ionic, we cancel out any like ions, which that is the definition of the last part. A spectator ion is an ion that appears unchanged on both sides of the chemical equation. So a complete ionic equation has spectator ions. A net ion equation, there are no spectator ions. Okay? We eliminate those from the equation. So that's what's the difference between complete and net. All right? So, moving into the steps, how do we then do this? Okay? The first step would be you write out your balanced chemical equation. You might have to predict the products. That might be part of it. You might have to predict the products. Then, based on solubility rules, you identify which compounds will be aqueous or will dissolve. You write these out as ions with the correct number of ions, so you include the coefficient, you include the charge. This will be called the complete ionic equation. Again, any solid, liquid, or gas compound will stay together and is written as a regular chemical formula. So if it's carbon dioxide gas, we wouldn't write this as C4 plus and 2O2 minus. It would just be CO2 gas. We will identify the spectator ions, so the things that are the same on both sides of the equation. We identify them, and then we basically cross those out and rewrite the chemical equation without the spectator ions. That is the net ionic equation. All right? So again, I'm going to show you in a minute how to go through it, and then you got it, it's another thing of practice, practice, practice with it. Again, the whole point is this is where we understand of, hey, as a chemist, if I end up mixing these two solutions together, what am I going to form afterwards? Will it still be a solution? I mean, there can be net ionic, there can be a situation where you write a complete ionic equation and everything stays dissolved. So then there would be no net ionic equation. There would be a blank. You'd actually say no net ionic equation. All right? But this will help you understand why things will precipitate out if you mix them together, and then how much should precipitate out, etc. We can go back to the conservation of mass with it. So we're going to start practicing, but again, if you need another good video, I'm going to have my video on here as well. But Bozeman Science obviously does an amazing job with this, trying to show it all off, if you want another resource with that. So let's show this, okay? This one's showing it kind of easy because it's already giving you the states of matter with it. Sorry, here we go. Okay, yeah, I'll leave that. Okay, but you have your equation. It is not, it is balanced. It's all balanced, so we don't really have to do that. We see 1Ag, 1Ag. This is supposed to be an arrow in the middle. Oh, shoot, that's in my spot where it doesn't work. So there's an arrow there. AgNO3 plus KCl yields AgCl, solid, plus KNO3, aqueous. So this one's already kind of helping you figure out without the solubility rules. So the complete ionic equation, I'm just going to write complete IE, would look like this. Ag plus NO3 minus plus K plus Cl minus produces AgCl plus K plus NO3 minus. So you can see all I really did was separate it out. We should technically write out all of the states of matter. These are all aqueous, 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 solid, aqueous, aqueous. So this is telling you, hey, when you mix these two chemicals together, all of them will spread out, or they're already ions, so they're all in the solution. But what's going to happen here is the silver and the chlorine will combine and form a solid, while the K plus and the NO3 minus will just continue staying in solution. So the K plus and NO3 minus are our spectator ions. If I said what would be the spectator ions, NO3 minus and K plus. So I eliminate those from my complete ionic equation to write my net ionic equation reaction. My net ionic equation would just be Ag plus, aqueous, plus Cl minus, aqueous, forms AgCl, solid. So that is all we got left with it. All right? Where those two ions combine and they form a solid precipitate. That is the real reaction occurring when you're mixing these things together. Again, the potassium and the nitrate end up really not doing anything. Like they said, they are spectators. All right, so let's, oops, I didn't mean to hit that button. Let's do another one. So this one I'll do a little faster. This one is not balanced. So I'll rewrite it. So if I have MgNO3 2 plus Na2CO3 produces MgCO3 plus NaNO3. There you go. So this one's not balanced, so I would balance it first. 1 Mg, 1 Mg, 2 NO3. I need 2 NO3s, 2 NAs. Now I have 2 NAs, 1 CO3, 1 CO3. I'm not like up top, I guess I'll write it in there. Aqueous, aqueous, so I mix two solutions. There's a solid that comes out, and then some of the last compound stays in solution. Almost all these are double replacement reactions as well. You know, we wouldn't really necessarily say, what type of reaction is this? It's going to be double replacement most likely. All right, writing it out now. Mg plus 2, aqueous, plus 2 NO3 minus. I do bring down the subscript and it becomes a coefficient because there's 2 NO3s in the solution. This still has to balance. I still need to show the same number of ions on both sides. So 2 Na plus aqueous plus CO3 2 minus 2 aqueous forms MgCO3 solid plus 2 Na plus aqueous plus 2 NO3 aqueous. My spectator ions, the things that stay in solution, are my nitrate and sodium ions. So those are my spectator ions. So the final net ionic equation would be Mg plus 2 plus 3 CO3 minus 2 yields MgCO3 solid. Again, the net ionic equation should also be balanced. Okay? Should also be balanced in charge if you look at that as well. The idea that this side has a total charge plus 2 minus 2 of 0. This is a ionic compound that's already neutral, so that's a 0 charge as well. Okay? Let's do maybe one more. Okay? All right, so I like this one because it doesn't have the products. So this is one where we have to think about it. So K3PO4. K3PO4 aqueous plus AlNO3 aqueous. Okay, so what I have here is, it's a double replacement reaction. So AX plus BY, it's going to form AY plus BX. So A is K, don't bring the subscript, and Y, NO3, plus AlPO4. Let's check the charges. Plus 1, negative 1, so that's the correct formula. This one's plus 3, negative 3, so that's actually the correct formula. Okay, sorry, this should be a 3 right there. NO3, 3. So now if I balance, 3 Ks, PO4, PO4, 1 Al, 1 Al, 3 NO3s, 3 NO3s. So we're balanced. All right. Now, the last thing we have to figure out is we have to figure out whether these are aqueous or insoluble. Well, K, potassium, that's an alkali metal. It's always soluble, so AQ. Nitrate's always soluble. AlPO4, phosphate is not soluble with aluminum, so that would be solid. So there you go. So then we write our complete ionic equation. 3K plus PO4 3 minus plus Al3 plus 3NO3 minus. This is 3K plus 3NO3 minus plus Al3, oh, nope, plus AlPO4 solid. Spectator ions, K and NO3. So I'm going to eliminate those. Oh, shoot, not PO4. NO3, K and NO3. And so I have, I'll write it as I have written here. PO4 minus 3 plus Al plus 3 yields AlPO4 solid. Okay? So hopefully you follow along with that well. Again, you're looking at, you need to think about the solubility rules. We're basically splitting everything up into ions for the complete ionic equation, unless it's a solid, liquid, or gas. There are problems where you might see water, liquid water in the products. You just leave it as liquid water, H2O. We balance the chemical equation, we split up into ions, and then eliminate the spectator ions. And that's the process that we follow. All right? Thank you very much.